So let's solve Dr. C number 1 from homework number 10. This is the exploding projectile problem where you're told that you launch a projectile of mass equals 9.6 kilograms from the ground, there's the ground, with an initial velocity or speed of 12.4 meters per second, that's V naught, magnitude, at an angle of 54 degrees above the horizontal. And the first part asks you to solve for where or what the maximum height is above the ground, the horizontal range, and the time it spends in the air. These are all questions that you should have been able to handle a month or more ago when we were dealing with projectile motion. The reason for starting with these is that later on we'll let the projectile break apart or explode in midair, and we'll want to analyze where the parts go. But what we will know is that the center of mass, or the original projectile, the center of mass will follow the normal projectile motion path. So let's start by analyzing it. Okay. So how do we do that? Well, let's start with, and you could start with any of these if you like, but I'm going to start by trying to figure out the time in the air. And I'll do that by recognizing that, given that y equals y naught equals 0 for the entire path, okay, time up and then back down to 0, that's equal to v naught yt minus 1/2 gt squared. Okay, that's, or you can think of it as y equals y naught plus v naught yt minus 1/2 gt squared. Okay, and this will give you time in t equals 0 solves this, of course, that's where you start. But the time in the air will also be a solution for this because that's when you're again at y equals 0. Okay. So this is an expression that, first of all, we can simplify. I can divide that out and get rid of that. We know v naught y, and I can solve for the time in the air equals 2v naught y divided by g, just rearranging this expression. This is v naught y, it's the y component, not the entire velocity, but the y component is given by v naught sine times the original theta naught divided by g. At this point you can just plug in your numbers, 2 times 12.4 meters per second times the sine of 54 degrees divided by g, or 9.81 meters per second squared, and plug that into your calculator, and you find the time in the air is just 2.05 seconds. Okay, so that's one of the things we were after. How about the range? It's easy once we've got the time in the air, because the range, or delta x, will just be the x component of the velocity times the time in the air. Remember, the x component of the velocity never changes. It's always equal to v naught cosine theta naught. There's no acceleration in the x direction. So just take that and multiply it by t. So we've got 12.4 meters per second, okay, times cosine 54 degrees to get the x component of the velocity, times 2.05 seconds. Plug that into your calculator, and you see the range is 14.9 meters. And finally, we want the maximum height. Okay, well, if it spends 2.05 seconds in the air and it starts at ground level and ends at ground level, from the symmetry of the motion, we know the maximum height, maximum h, occurs at time in the air divided by 2, or 1.025 seconds. I'll just keep an extra significant figure along for now because it's easier than figuring out what to do with the 5 here. And so we can solve for the height at time t equals 1.05 seconds with the equation of motion in the y direction, y equals y naught plus v naught yt plus at squared, plus 1/2 at squared, but that's minus g for the acceleration, so minus 1/2 gt squared. Remember, this is 0, it starts at ground level. So I just have to plug in all the values for these quantities, and we know them all now. It's 12.4 for v naught y times the sine of 54 degrees to get the y component, times 1.025 seconds, minus 4.9, it's 1/2 g meters per second squared times the time squared, seconds squared. So just plug all that into your calculator and you find the maximum height is 5.1 meters. So that's part A. That's all we need to do for part A. Now we get to the interesting thing. Okay, at the peak of the motion, okay, so the projectile is going up here, and at its peak it splits into two parts, exactly in half, okay, and one piece just falls straight down while the other continues. It won't continue along the original parabolic path. It will, at least may do something different, okay, and I'll predict that if this falls straight down, then for the center of mass to continue here, the other half will have to go further because of the explosion. Okay, so what we are asked to do though is find where this piece lands and fall straight down. When and where does this piece land? That's actually pretty easy. You don't have to do any work if you don't want to. At its peak of the motion, if it's halfway along the range, okay, so it's going to land at where it was in the x direction at r over 2, or 7.45 meters. Just take this and divide it by 2. Okay, when does it land? Okay, relative to the launch, well, now we have to figure out how long it takes to fall straight down from here. And again, if you're clever, you don't have to worry about that because we know how long it took to get up here. And remember, all we're worried about is the y component of the motion. If it takes a time t to go up to this distance with the acceleration of gravity down, it takes the same time to fall because we're not giving it any additional or less vertical component of velocity when the explosion happens. So all you have to do is say, oh, it takes it 1.025 seconds to get up there, half of this quantity. So it's going to take 1.025 seconds to get back down. And so the time is 1.025 seconds to get back down. Now that's just the time to fall from here, but it also took 1.025 seconds to get back up, to get up there in the first place. So the total time for it to fall is the same time it takes for this to reach the ground, because we haven't changed anything about the y component of the motion. So they'll both land at the same time. Okay, so the overall time is just 2.05 seconds again, the same value we had for this. Okay, remember, these two pieces must land at the same time, so the center of mass stays between them. Its motion doesn't change, and so they both have to land at the same time. So really, part B was pretty easy if you understood center of mass motion. It was pretty easy because we had, at the explosion, we said it's split in half, and this one stops and then falls down. If this one had been thrown up in any other direction, the problem would have been a little bit harder, as we'll see in part D. And then part C asks, where does the other piece land? It's the piece that gets projected forward by the explosion. Okay, but we don't have the details of the explosion, but we don't need them because we know what happens to this piece. we know what happens at the center of mass. We also know what happens at this piece. Again, has to land at the same time because the explosion did not change, okay, the vertical component of the motion of the center of mass, or of either piece actually. Okay, and where does it land? Well, if this piece lands this distance short of the center of mass, this piece must land this distance further than the center of mass would have landed, or if the projectile hadn't exploded, where it would have landed. Okay, so what's this distance? This distance is r over 2, or 7.45 meters. Okay, and so this piece is going to land at a distance r plus r over 2, or 14.9 plus 7.45, which is going to be equal to 22.4. And here I'm just rounding off the 5, if you like, to 7.5 for 3 significant figures. So 22.4 meters. So that's parts A, B, and C of this problem. Now we come to what is the hardest part of this Dr. C problem, which is D. Okay, instead of exploding at the peak and splitting the projectile in half, okay, it's going to explode at some other point. Okay, so here's the path of the center of mass, or the projectile if it hadn't exploded. And what we know is after the explosion, one piece is here, a 6.5 kilogram piece is somewhere described by at 1.42 seconds. It has a value of y equals 5.9 meters, and the value of x equals 13.6 meters, all measured from the origin, which is where you launched the projectile. And so now you have to find the location of the other part of this, okay, and find out whether it's hit the ground yet. Okay, so to do this, remember, our basic principle is we know what happens to the center of mass. If we know where the center of mass is at this time, and we know where this part of the projectile is at that time, we can use the center of mass formula to find where the other part of the projectile is at that time. So our first step is to find the position of the center of mass. Where is the center of mass at t equals 1.42 seconds? Well, again, this is a standard 2D projectile, or just a standard 2D motion problem. So the position of the center of mass equals v naught x times t, okay, because x naught is 0, okay, and it moves at constant velocity, or v naught cosine theta naught t. Plug in your values, 12.4 meters per second, cosine 54 degrees, 1.42 seconds. It's at 10.35 meters in the x direction. The y component of the center of mass, it's equal to y naught plus, but the y naught is 0, so I'll leave it out. That's just v naught yt minus 1/2 gt squared. Plug in all the values for these quantities, 12.4, sine 54 degrees, I'm leaving out units for now, 1.42 seconds minus 1/2 g is 4.9 meters per second squared, 1.42 seconds squared, and the y component is 4.365 meters. So we know the position of this piece of the mass at this time, and we know the position of the center of mass this time. And now I can find the position of the other piece, but let me just point out the mass of the other piece equals the total mass, or 9.6 kilograms, minus the mass of the piece we identified just above. So 3.1 kilograms is the mass of the other piece. The basic concept I'm going to use is that in general, the position of the center of mass, sort of combining x and y components in R, equals m1 r1 plus m2 r2 divided by the total mass. But let me rewrite this in a slightly more convenient form that I'll use. Just m1 plus m2 times the position of the center of mass equals m1 r1 plus m2 r2. So that's the vector form of this equation, but I've got to break it down to components. So let's deal with the x component first. Okay, the total mass is 9.6 kilograms. And the position of the center of mass, our center of mass, at least the x component, we worked up here, is 10.35 meters. That has to be equal to the mass of the first piece, whose position we know, 6.5 kilograms. And we're told 13.6 meters is where it's at. That was given in the problem statement. That's where it's at this given time. Plus the unknown position of the second piece, and its mass is 3.1 kilogram. So these are all terms that we know except for x2, and x2 is what we're solving for, but now we can do that. x2 equals 3.54 meters. Just plug that into your calculator and do a similar calculation for the y component of the motion. Okay, 9.6 kilograms. And we know at this time it's at 4.365 meters. Okay, because we calculated that up here. That has to be equal to the mass of 1, 6.5 kilograms, times its y component, 5.9 meters, as given in the problem statement for the position of this part of the projectile, plus the unknown y component of the missing piece, or second piece, times 3.1 kilogram. So again, you have all these numerical factors and the unknown y2 that we're trying to solve for, and so we know its position. Okay, that's 1.15 meters. Okay, so now we have answered the question, what is the location of the second fragment at this time, t equals 1.42 seconds? And then you just have to ask whether it's hit the ground yet. y2 is greater than 0, which is still in the air, hasn't hit the ground. If it hit the ground, y2 would be 0 or even a negative number to indicate it would have been below the ground if the ground hadn't stopped it. So that's Dr. C number 1.